In this video, we'll explore how to machine a 5-axis index part, also known as 3+2 machining, using EZCAM software. You'll learn how to process how correct coordinates are sent to the machine through the post-processor. We'll also take a brief look at FANUC's G68.2 tilted workplane system to understand both its theoretical background and its practical application. If you're using a standard 3-axis machine, there's usually no need to define a tilted workplane. But once rotary axes, such as B or C, come into play, things become more complex. When machining different faces of a part, the coordinate system must be realigned each time. In the past, there were two main ways to solve this. The first was to use separate work offsets, like G54, G55, or G56, for every new surface. That method worked, but it was time-consuming and increased the risk of human error. The second approach was programming relative to the rotation center, meaning all surfaces were defined relative to the intersection of the rotary axes. This method was more consistent, but even small mechanical inaccuracies or zero-point errors could cause deviations. To overcome these limitations, FANUC introduced the G68.2 tilted workplane command. With this system, there's no need to manually redefine coordinate systems each time the part is rotated. The control automatically calculates and applies the transformation for you. Thanks to G68.2, you can program operations on angled surfaces as if the part were lying flat on the table. There's no need for complex trigonometric calculations. Toolpaths are applied directly and accurately to the tilted plane. You can choose any point, on or near the part, as the rotation origin. The control system automatically calculates all required rotations and coordinate transformations. As a result, you can program even complex surfaces as easily as flat ones. There's no need to manually reset tool zeros or work offsets. The control takes care of everything. In this section, we'll show the predefined UCSs, or user coordinate systems, prepared on the part. These UCSs correspond to the various sides and angles used in the following operations. Let's take a closer look at the command structure. The X, Y, and Z values define the pivot point or rotation center. In most cases, they're left as 0, meaning the rotation center matches the part's origin, but they can also be placed anywhere, for example, at the center of a face or a hole. The I, J, and K parameters define the orientation of the new Z-axis, the normal vector of the tilted workplane. In other words, they determine how the new machining plane is positioned in 3D space. These values are computed by EZCAM according to the desired Z-axis direction of the tilted coordinate system, following FANUC's Euler angle rotation sequence. For example, tilts the plane 45 degrees around the X-axis. First rotates 30 degrees around the Z-axis, then tilts 45 degrees around the new X-axis. The control automatically calculates the corresponding angular transformations based on the machine's kinematics and commands the rotary axes A, B, or C to achieve the correct alignment. This eliminates the need to manually specify individual rotary motions. You simply define the desired plane orientation, and the control handles the rest. Now let's take a look at how the operations we see on the screen are created. We start by placing our main coordinate system, or world, anywhere on the part. Using the coordinate system by geometry command, we define the X and Z directions by selecting surfaces and edges. Then through the world UCS on model stock interface, we can easily move this coordinate system to any position on the part. In 5-axis index machining, the main difference from 2.5D or 3D operations is simply the need to create additional coordinate systems and select them within the operations. We'll use the main coordinate system for operations like facing, contour profiling, and drilling on this plane. Next, let's machine the chamfers at the corners using a centerline pass with the selected tool. For that, the surface must be positioned perpendicular to the Z-axis, allowing us to use the flat bottom of the cutter. So we'll create a new coordinate system for this orientation. The name we give this UCS doesn't matter technically. What matters is that it's positioned correctly. Now, should we place this new coordinate system at the same point as the main one, or directly on the surface wheel machine? In fact, both approaches work equally well. The G-code will include the positional difference between the main and machining coordinate systems automatically. So you can place the new coordinate system anywhere, as long as its Z-axis orientation is correct. Let's continue by placing it on a convenient spot near the region to be machined. For this corner, since the tool diameter is large enough, we can perform the operation with a centerline pass. Inside the face operation, simply enable the centerline cycle option and select the surface you wish to machine. Important note, when you look at the MCS-ID field, you'll notice that program automatically assigns the currently active coordinate system whenever a new operation is created. Of course, the user can always select a different UCS manually from the drop-down menu if needed. We then repeat the same process for all other surfaces that require machining at different orientations. As you can see, indexed 5-axis programming in EZCAM is straightforward. All you need to do is create new coordinate systems to view each region at the correct angle, and the rest follows the same standard operation steps you already know. After reviewing the simulation of all operations, look at the G-code output. You'll see that in the program generated for the FANUC RoboDrill DL21A5, all plane rotations are correctly handled by the G68.2 command for each setup.